Hi everyone, my name is Shravan Hanasoge. I'm a faculty member at the Department of Astronomy and Astrophysics at the Tata Institute of Fundamental Research in Bombay. And today we're going to be talking about the Sun, specifically helioseismology, which allows us to view the interior of the Sun. So let me begin by the most obvious aspect of the Sun, which is its magnetic field. So this has been seen as early as 2,500 years ago by the Chinese. And here's an image in a more contemporary image that contains the magnetic field captured by the Michelson Doppler imager, which is an instrument on board a satellite called the Solar and Heliospheric Observatory. And what you see is a range of magnetic fields at different scales and of different magnitudes. So you see the white coloring on this image is the field that's coming out towards us, and the black is the field that's going into the Sun. So you could think of it as field lines that are emerging from the surface and then disappearing back inside the Sun. And you see these large areas, and you see these tiny sprinkled, what they call salt and pepper type magnetic fields. And so this plethora of scales is a mystery, continues to be a mystery today. When we try to understand what creates these magnetic fields and how they're sustained, how they're generated, and so on. So here is a nice movie of the magnetic field evolving over a month, or 28 days is roughly the solar rotation period. And you see field emerging to the surface, evolving, and so on. So this undergoes periodic modulation on the scale of 11 years. And so this is how we encode this particular feature of the Sun. On the bottom plot, you see these butterfly type features. This diagram is known as a butterfly diagram. The horizontal axis is time or date, and the vertical axis is latitude, as you see on the Sun. So for instance, the bottommost point of this image on top, or the video on top, is at a southern latitude of 90 degrees, and the topmost point in that image is the northern latitude of 90 degrees. And you see a very remarkable feature that basically most of the magnetic field is in these small latitudes of plus minus 30 degrees, i.e. 30 degrees in the south and 30 degrees in the north. And so this is captured in this butterfly diagram. Every time you see a sunspot or a magnetic region, you place a little dot on this figure. And so as it moves across the surface of the Sun, you see, you make sure that you're putting a dot essentially as a function of latitude. You see a magnetic region, you put a dot there, and you plot that as a function of time, and you see where magnetic fields at what latitudes they're emerging. So it turns out, interestingly, that all magnetic fields start appearing at these relatively high latitudes of 30 degrees at the start of the cycle, and as the cycle evolves, they appear to move closer and closer to the equator. And towards the end of the cycle, they're appearing almost at the equator, and then it stops, and the magnetic field seems to stop, takes a little break, and then the whole process begins again. And so this is of great interest in what drives the cycle, what creates the structure, is an outstanding question and remains unsolved. And solar magnetism is not just a beautiful and intriguing piece of physics at the surface of the Sun, but also affects us. So as I said, there's an 11-year cycle, which is, you see those butterflies. That seems to happen every 11 years. And so what's really interesting is that you can go back nearly 10,000 years by drilling ice cores and looking for specific isotopes that are sensitive to cosmic rays. And during periods of high magnetic field, the entire heliosphere is sheathed by the magnetic field of the Sun, and cosmic rays are deflected away. In times of solar minima, there is no strong magnetic field covering the heliosphere, and cosmic rays do reach the Earth, and then they affect the magnitude of or these the composition of these different isotopes. And so by measuring these isotopes, the isotopic content in ice layers, you can go back in time and try to calibrate that to the activity or the extent of magnetism on the Sun. And by doing this, you see a very remarkable feature. So in the uppermost plot here, you're seeing this calibrated solar activity as a function of time in going back nearly 10,000 years. And you see that there are only 2 times in the entire last 10,000 years where magnetic fields have been as high as they are today, or they were in the previous century. And that's now, or when I say now, I mean the previous century and nearly 9,000 years ago. And so it's very remarkable that the previous century has had an unusually high amount of magnetism in the sun, and we try to understand what's causing this type of behavior. And the other remarkable thing is that the UV content, every time there's a magnetic maximum, i.e. when there's a lot of magnetic field on the sun, it makes the sun more transparent for technical reasons that I won't get into here, and the UV content, the ultraviolet content of the sun, increases nearly by 30%. And this is thought to be relevant to some changes on Earth's climate. And so we try to take a lot of these things and understand their impact on Earth's climate as well. But focus of this talk is not so much how it affects us practically on Earth, but the physics of what's driving this large-scale magnetism. Here are many fundamental questions about solar structure. What is convection? So convection is the transport of heat by fluid flow. And so what is the form of convection in the outer envelope of the sun? And I describe this in greater detail. The sun has complicated large-scale flows known as differential rotation and meridional circulation. I'll explain these as well. And we don't know where they're coming from, what's driving them. So what's ultimately, all of these questions lead to the question of what's driving the solar dynamo. Where is the magnetism of the sun being generated? Where is magnetic field being cycled, and so on. A dynamo, by the way, is a self-sustaining magnetic field. If you had, let's say a star, if you had a ball of fluid, it's generating its own magnetic field, but also sustaining it over very long periods of time. That's what's called a dynamo. And we don't understand what drives a dynamo, what are the processes that make this possible. Are there internal gravity modes in the deep interior? This is a slightly more technical question that I will come to towards the end of this talk, and it gives us insight into what's happening in the core and the deep interior of the sun, which are generally inaccessible by almost any other means. So this little plot at the end, this little cartoon, tells you how convection, which as I said is the transport of heat by fluid motions, drives so many important physics and has many practical and scientific consequences. And I'll describe some of these as the talk proceeds. So here is the basis of seismology. Sound waves are excited by the sun in the outer layers by convection. And so you see this little cartoon image that shows the behavior of sound waves. And sound waves are, as you know, pressure is the restoring force. And so in the fluid, you have these turbulent convective motions right at the surface. These are exciting sound waves. And these waves propagate inside the interior, where the increasing sound speed is essentially causes them to deflect away from the center and reappear at the surface. And so you see these beautiful shapes in this plot, where waves, they proceed first into the interior and then they re-emerge back up to the surface. And there's a variety of waves. There are waves that are stuck mostly near the surface layers, like you see the blue line. But there are other waves that go very deep inside the interior of the sun, like these red waves. There are indeed even modes that cause the entire sun to, they're called the breathing modes of the sun, to compress and expand. So those are the ones that go right up to the very center of the sun. And so how do we know these waves exist? Well, these waves, as they propagate into the interior and come back up to the surface, cause the surface to modulate a little bit. They displace the surface. And when this happens, the absorption lines, there are a sequence of electromagnetic absorption lines that are formed at the surface. We track these, satellites track these. And when the surface is displaced by a small amount, these absorption lines are Doppler shifted with respect to us. So they're either red shifted or blue shifted, depending on how the fluid at the surface is moving. And by calibrating these motions, by calibrating these Doppler shifts, we determine the velocity field at the surface. And that gives us the fundamental unit of seismic measurement, which is the solar surface velocity field. Using that, we can then infer the properties of the interior. And so here is a little video that shows, taken by the Michelson Doppler imager again, that shows how the surface velocity wave field is evolving as a function of time. And you see this, it looks like it looks like your TV screen when you just have background static and you don't have any signal. And you can see it scintillating, and these are waves basically. These are acoustic waves in the sun. And the fundamental concept of helioseismology is illustrated in the top movie here, which is that you use different sets of modes to image different parts of the interior. So the basic measurement, as I said, described in the previous slide, is the surface velocity wave field. But how then do we go from that point to actually making inferences about the interior of the sun? And this is a complicated process, but conceptually this is what we do. First, we take the measurements of the surface, which is denoted unfortunately by the same symbol 2 times, but bear with me please. So you have phi, which is the signal that you measure at the surface. That's the velocity field. That's a function of latitude theta and longitude phi, and as a function of time as well. And so this is a quantity that we measure. We then take that quantity, perform a spherical harmonic transform in space. So the theta and the phi, they get transformed into L and M. L is spherical harmonic degree, M is azimuthal order, and the T gets transformed to frequency, temporal frequency omega. So we write this as phi superscript omega subscript k. K refers to L and M. And this is sort of a most critical quantity, this Fourier space quantity, to create many products, to do the analysis of modes and so on. So these modes are then classified using 3 quantum numbers, n, L and M. N is radial order, L is spherical harmonic degree, as I said, and M is azimuthal order. And the number of nodes in radius of so if you have a mode, then it has an eigenfunction, and eigenfunctions have nodes. So you can think of a sine wave, for instance, has every time it crosses a 0, it's a node. So the number of nodes, every 0 crossing that you have as a function of, in radius, that's classified as, or that's denoted using the radial quantum number n. So if you have 0 crossings, you have no crossings at all as a function of radius, that's called n equal to 0, and that's called a surface mode. And then if you have deeper waves which with a finite number of crossings, those are n equal to 1, n equal to 2, and so on. Similarly, L denotes the number of crossings as a function of latitude, and M, the azimuthal order, is the number of crossings as a function of longitude. We take this phi omega k that I described earlier, you take the modulus squared, and then you plot that, you average over all the azimuthal orders M, and so you're left with mod phi omega subscript L squared. So that's what is known as the power spectrum. And the vertical axis of the plot on the right is temporal frequency, and the horizontal axis is the angular degree, the spherical harmonic degree, L. And you see tremendous structure here. You see some non-trivial structure, and these are the normal modes of the sun. The red indicates regions of high power, and the blue indicate regions of low power. And you see that ridges have been you see the structure with all these ridges basically placed one on top of another, and these refer to different radial orders. The lowest ridge is n equal to 0, the highest ridge is n equal to 25 maybe, and you have a range of different L's, harmonic degrees, that have all been excited, and so these are all the normal modes of the sun. And we measure millions of these with great precision, and we're able to label all of them, and we know what modes they are. And by, as I said, combining different modes, you can image different layers inside the solar interior. We start with the wave equation to this wave propagation in the sun. To a very good approximation, wave propagation in the sun is well described by the linear wave equation. And so this basically means that the amplitudes of waves is very small. It's a small amplitude approximation. So in that limit, we can derive what are known as Green's functions, which are impulse responses to the wave operator. And so the wave equation in a very abstract generalized form is given as the very first equation, which is Lg equal to I delta. L is the wave operator, G is a Green's function, I is the unit dyad, and delta is the delta representation, delta function representation. L xi, where xi could be any variable including G, is given by this complicated expression here. The first term is inertia, where omega is temporal frequency, rho is density. Minus I omega rho gamma is the second term, refers to attenuation, where gamma is uppercase gamma is attenuation. The third term is advection due to flows, so V is a flow velocity vector. The fourth term contains the response due to sound speed and pressure gradients, as you can see. P is the pressure gradient, C is the sound speed, and so that's the pressure restoring force. It's critical for all acoustic waves in the sun. The fifth term refers to buoyancy. The sixth term and the seventh term refer to Lorentz stresses, that is magnetic fields and how they impact wave propagation. So B is the magnetic field, G is the gravity. Now once you have this wave operator, it is what is known as a self-adjoint wave operator. There are certain class of operators and they have very nice properties. It's like symmetric matrices. And self-adjoint operators have a beautiful property that they have a complete eigenfunction basis. And in particular, if you look, you can take this operator and you can think of it in two ways. You can think of its spectrum. A spectrum is known as the set of eigenvalues and eigenfunctions of that operator. And secondly, you can look at Green's functions to that operator. So there are two broad ways in which seismology, not just helioseismology, but all seismology is constructed. Now the spectrum of this operator contains, as I said, eigenvalues, omega k, as these are all the eigenvalues, and the eigenvectors, xi k. So if you had a model of the wave operator, then you could determine its eigenvalues and eigenfunctions. And then you measure, let's say, the eigenvalues. As I said in the previous slide, we can measure all the normal mode frequencies of the sun. So we have observed eigenfrequencies and we have predicted eigenfrequencies, and the difference, delta omega k squared, as you can see, they tell you the difference in the eigenvalues from predicted and observed tells you something about what's going on in the solar interior. Similarly, you can do something much more complicated, which is by measuring differences in the eigenfunctions from the sun and from theoretical predictions, and those give you what is known as mode coupling. There's probably not a lot of time to discuss in detail each of these techniques, but there's a great deal of mathematics and complexity involved in this process, which I'll try to give you a very broad impression of. Now the second way to proceed is to look at the Green's function of this operator, and the Green's function here is essentially connected to the eigenfrequencies and the eigenfunctions, but it's a different approach. And that allows, and you look at a predicted Green's function, you look at a measured Green's function from the sun, and then you try to interpret the difference, delta G. And these techniques, such as time distance and holography and so on, these techniques tell you, give you access to properties of the solar interior as well in a different way, which I describe. So now we have these normal mode frequencies or these global mode frequencies that I described. These are the eigenvalues to the solar wave operator. And so these normal mode frequencies, as I said, can be used to determine the structure of the interior of the sun to great precision. So after doing a great deal of work, which I will not describe here, I just want to describe two or three of these major results and a broad understanding of what the sun's interior looks like. We know now that the core of the sun is at extremely high temperatures on the order of 15 million Kelvin, very dense, and where hydrogen is burnt to form helium. During this process of nuclear fusion, a lot of electromagnetic radiation is released. This is essentially what creates the sun to be luminous, what causes the sun to be luminous and creates solar energy. from this measurement of this core temperature, which we have constrained fairly accurately using helioseismology, we have bounds in the neutrino flux. Because we know about the nuclear fusion reactions that are happening in the core, we can estimate the neutrino flux, which then can be used to understand the properties of neutrinos. This has led to two Nobel Prizes being awarded over the past decade or 20 years or so that have attempted to understand the physics of neutrinos. So these have been major results that have been supported through helioseismic constraints. The second major structure result is the depth of the convection zone. It tells you how deep the outer layer of the sun, which is undergoing convection, is. So when nuclear fusion occurs, you have a tremendous amount of heat that's generated. This heat is transported outwards by the movement of photons. Photons are being continuously scattered, but they're gradually moving outwards through what is known as the radiative interior. By the time you get to 0.7 or 70% of the solar radius, the plasma is sufficiently cool that radiation is no longer as successful a transport or as efficient a transport mechanism, and at that point convection takes over. So this is a very important result from helioseismology that's given us access to the depth of this convection zone. And so the outer 30% of the sun is undergoing convection, and these convective layers give rise, it is thought broadly at any rate, to many of the complex dynamics of the sun. Now we have frequencies, as I said some slides ago, and by studying these frequencies, specifically an aspect known as degeneracy. So what happens is, if you're looking at a specific frequency, if the sun were a quiescent ball, non-rotating quiescent ball, then all the eigenfrequencies are well enough described by just two quantum numbers, radial order n and spherical harmonic degree L. But the moment you have rotation, then this lifts this degeneracy. Then you have three quantum numbers, radial order n, spherical harmonic degree L, and azimuthal order m. And what happens is, waves that are going along the direction of rotation are sped up, waves that are going in the opposite direction to the rotation are slowed down. And so you have this, what is known as lifting of the degeneracy, and you have three quantum numbers then that start to play a role. We know that for the sun, since rotation is an important and significant phenomenon, there is the lifting of degeneracy is strongly connected to rotation. And so by measuring the amount of degeneracy lifting, we can infer the structure of rotation, and a very remarkable result comes out. We can measure solar rotation as a function of of radius and latitude. We find, first of all, that the equator is rotating faster than the poles. So this is a very remarkable result. Secondly, we find that as you go deeper and deeper inside the interior, that these rotation contours are approximately aligned along with the radius. So you see this plot on the left, the upper left plot, that contains the rotation rate, that plots the rotation rate as a function of latitude and radius. These are contours of constant rotation, and on the color bar indicates 300 to 450 nanohertz. So that 440 nanohertz is about 26 days is the period of rotation, and so you see that 26 Earth days, that is, and so you see that the equator, the contours of rotation at the equator suggest that it's rotating at a higher speed than the poles. But what's again interesting is, as you go towards the deep interior, let's say below 0.7, the rotation transitions to nearly solid body. And so this is very, very interesting, that you have a convection zone that is differentially rotating along contours, isocontours that are aligned with the radius, but a deeper interior that is rotating like it's a ball or a solid body. Now, the reason why it's so interesting is this is contradicted by both theory and simulation. Both theory and simulation suggest at first order that these rotation contours are aligned or parallel to the rotation axis. As you can see in the plots on the right, you see all of these lines, these are rotation contours that are parallel to the rotation axis. These are very different from the contours that you see on the left plot, which show that they're strongly inclined. And so this remains an outstanding puzzle, and we don't know what drives differential rotation to take the form it takes. So now I move on to a different topic. Now this, so far, the past 2 slides were the study of eigenfrequencies of the sun. And so this is going back to to the broad categorization that I had discussed. The first part of it, which is to look at the spectrum of the operator, that was I just described 2 major results from that particular approach. Now we discuss what changes to the Green's function can tell you, and that forms an entire discipline in subdiscipline in helioseismology, known as local helioseismology, which enables, as the title says, the imaging of local or regional and non-axisymmetric structures in the sun. So let's go through a brief history. So we go back to the discovery of acoustic waves in the sun, which is in 1962. In that paper, which is very remarkable, the author has already seen the case for local helioseismology. The author of that paper suggested that you could image the localized structures, and you can do all of these remarkable things, and which really were not possible till only very recently. So the first major technical development happened with the measurement of normal modes and the development of these theoretical techniques known as global helioseismology, which enabled the measurement of internal structure and differential rotation of the sun, which I've just described. Once these major developments occurred, we started to look at smaller things. And if you remember from one of the first 2 slides, you saw sunspots, which were very localized features. So the question was, what's driving these? What's underneath the sunspot? And so on and so forth. And so there were a number of techniques that were introduced, like ring diagram analysis, and then there was normal mode coupling, there was time distance helioseismology, which measures the travel times of waves, and then acoustic holography most recently. And each of these techniques has led to the measurement of very important aspects of the sun. None of these have been set in stone yet. We're still improving these techniques because the sun is a complicated oscillator where convection and magnetism are still playing an important role in the physics of oscillations. So we're still continuously improving theory to understand and measure these circulations better. But these set of results described here are some of the most important results to come out of helioseismology. So I want to describe 2 techniques in this talk. The first technique is time distance helioseismology, which refers to the measurement of and the use of travel times of acoustic waves to infer the properties of the interior. So the most important thing in this is that you take the velocity signal at 2 different points, 2 different spatial points at the surface, and you cross correlate them in time. So you have a signal 1 and you have a signal 2, and then you temporally cross correlate them. When you do that temporal cross correlation, you measure something that looks like the bottom panel, the broad bottom panel here. So to go one step back, if you recall, I said that there are these ridges. So the top left refers to different ridges. There are the P0, P1, P2. P0 is also known as the F mode or the fundamental mode. And so these refer to different numbers of radial orders in these modes. And you can isolate different modes. For instance, in this case, we've isolated what is known as the F mode or the P0 mode, and only that mode appears on the top right panel. And so once you isolate that mode, which is done by taking the data set that you have and applying a filter to it, a spatiotemporal filter. This is all done in frequency domain. Then you come back into the temporal domain, and then you can perform a cross correlation. And so this is between 2 points. You do a temporal cross correlation, and you see as a function of time lag on the horizontal axis, it's measured in minutes, and the vertical axis is a normalized cross correlation. And you see 2 broad features at positive time lag and negative time lags. So let's consider the points to be A and B. So if a wave were to go from A to B, then that would show up in the positive time lag branch on the right. So the bottom panel on the right half of this plot. Now if a wave to go from B to A, then you would measure a cross correlation branch on the left of that to the negative time lag. So basically what this says is that waves are propagating from A to B and B to A, and you see these cross correlation branches. So this is the fundamental measurement process, and then we isolate different parts of this cross correlation measurement to make inferences about the interior. So in this case, the two windows are saying that I'm going to look at these two parts of the cross correlation diagram to try to understand what I can say about the interior. Why is this useful? Well, if you think about waves, if you think about, let's say, a bat or a human being walking into a dark room, and let's say you shouted, then the first thing you would do is if you would listen to, unconsciously at any rate, you would listen to the travel time of the wave. You would wait for the wave to go reflect at let's say a far boundary inside the room, and the wave reflects and comes back to you, and you wait for that time, and you measure, your brain measures that travel time, and then you think, oh well, I know the size of the room based on how long it's taken for the wave to go and come back. So in some sense, what you know instinctively is the speed of sound in air. And from that, you've calibrated, your brain has calibrated the time that it takes for waves to travel. So in the same context, and this is what bats do as well, bats construct complex images of their surroundings using travel time measurements, basically. And so similarly, we can apply this technique to understand what's going on inside the sun. We measure wave travel times using these cross correlation measurements that I just described. You can also use amplitudes, but the most important thing is the wave travel time. This is, as I said, for the reason that I just described, is that the significant and signal feature of a wave is its phase. And so in the sun, we have three types of speeds. We have the simplest thing, which is the sound speed, and this is isotropic, which is to say that the sound speed is independent of the direction in which the wave is propagating. So from the sound speed, we get estimates of temperature fluctuations inside the sun. The second, slightly more complicated speed there is through flows. So imagine that there is rotation and you have a wave. If the wave is going in the direction of rotation or on that flow, let's say, then it's sped up, so its travel time decreases. If the wave is going in the opposite direction to the flow, then its travel time increases. And so there is a breaking of symmetry in the direction of propagation. If the wave were going perpendicular to rotation, it's probably not going to sense a rotation, and so it won't really have any travel time shift. So in that sense, it's symmetry breaking and depends on the angle of the wave with respect to the flow. And so from this symmetry breaking, we can measure large and small scale flows inside the sun. The third and most complicated measurement is that of magnetic fields. These basically change the speed of the wave depending on the direction in which the wave is propagating, and they have a very complicated tensor nature which essentially splits waves into alphane, slow and fast magnetic waves. There are three different types of waves, all propagating at different speeds and have different group and phase velocities, and in principle we can also infer this from the wave propagation properties. These are the three types of broad sound speeds that we have for waves in the sun, from which we infer sound speed, flows, and magnetic fields inside the interior. So time distance helioseismology in particular, and acoustic holography to some extent as well, has led to very significant advances. One of them is the study of meridional circulation, which I described early on in the talk. Meridional circulation is an equator to pole circulation. You can see that plot on the left, and thought to be very crucial for solar dynamo processes. So flow basically starts from the equator, goes to the pole, submerges, and then at some depth inside the interior turns back around and comes back to the equator. And now whether there is a one cell or a two cell or multi-cell meridional circulation remains an outstanding question. And this particular plot on the left, you see, is a two-cell meridional flow, and so there's a cell on top and there's a cell at the bottom, and there basically was an inference from some years ago this is still a subject of open discussion, and there's still quite a bit of work to be done in this regard. The second plot, the middle plot, was a controversial and also of major interest to helioseismology, because it helps constrain the properties of convection in the interior. As I described in the beginning, convection is critical to many external processes of the sun. So you see in this plot, the solid lines at the bottom are from helioseismology, and the dot dash lines on top are from numerical simulation. The horizontal axis is spherical harmonic degree, vertical axis is the velocity amplitude of convection. And so you see that helioseismology is suggesting that those flow velocities are much lower than numerical simulations predict. And this represents a major challenge in understanding the physics of what's going on with regards to differential rotation and the solar dynamo itself. This is a controversial topic still under intense scrutiny, and considerable work is ongoing in this regard. The third major result to come from time distance helioseismology, and perhaps acoustic holography as well, is the emergence of new magnetic field. As you may recall from one of the first movies that I showed you of magnetic field appearing at the surface and evolving, there is constant new flux arriving at the surface, and we don't have an ability yet to predict when magnetic field will emerge and of what size and what speed at which they emerge. And so helioseismology can be used to constrain some of these properties, and a major result in this regard appeared a few years ago on this, and they constrained the velocity at which magnetic fields rise from the deep interior up into the surface. So my very last topic that I'm going to describe is normal mode coupling. It's a cutting edge topic that my group at the Tata Institute works on. And normal mode coupling, again, as I described earlier, is looking at the spectrum of the operator, which is the eigenfunctions. And so we start with a reference model. A reference model is a simple model which is non-rotating, it does not have convection, it's axisymmetric, which is to say that you could rotate the reference model as a function of longitude and you would see no difference, and it also does not have magnetism. Clearly all of these are wrong, because the sun is rotating, it has convection, it is non-axisymmetric, and it has magnetism. And as I described earlier, linear theory for wave propagation works very well. And so for this reference model, we have a complete set of eigenfunctions. And for the sun, you have a set of some eigenfunctions that are different, because all of the properties of the sun are different from those of the reference model. But because the set of eigenfunctions of the reference model is complete, we can express every eigenfunction of the sun as a linear combination of the eigenfunctions of the reference model. And there are these constants, or these weights or coefficients, alpha, superscript k prime sub k. These are known as coupling coefficients. And so the eigenfunction of the sun is a weighted combination of the eigenfunctions of the reference model, and the weights are known as coupling coefficients. From these coupling coefficients, we can find an inverse problem, or we can construct a problem that connects the reference model to the sun, and you can determine all these properties such as rotation, convection, magnetism, and so on. And it's a very powerful technique. It has many advantages. You can model the noise, the background noise of these measurements very accurately. You can apply time varying perturbation theory, which is to say that the sun is a time varying system, and these measurements automatically take that into account. You can take into account systematical errors in the instrument itself, and there's very little data manipulation in this, and there's a huge amount of beautiful theory that supports this, very elegant theory. And the method has been validated, and we've detected, for instance, Rossby modes in the sun, and independently verified by another detection by Lerpti and et al. So it's in some sense a well verified technique, and it has considerable promise in this regard.